Welcome AP Chem students. It's the first pod lecture of 2012. Can you believe it? It's going to be an exciting year for some of you seniors in the classroom. And this is going to be our first podcast on chapter 11. Sounds like I need to start learning how to talk. And we are going to be talking about solution composition. And solution composition is something that really applies a lot to our everyday life. And so hopefully you'll be able to make some references to that when we talk about some of these things. Now there's a lot of different pieces that we're going to be doing in class, so we're going to be kind of jumping around on these lecture notes. So the first thing we're going to take a look at is the various types of solutions. And if you take a look at these examples that we have down here, you guys can see that these examples listed are some things that you are familiar with. Now if we think about the state of the solution, so the state of the solution, whether it's dilute or concentrated, you have to remember that when we say the word solution, that we are actually referring to two parts. Remember, we have the solute, and we always have to have the solvent. And if you recall, the solute is the substance that is being dissolved, and the solvent is the substance doing the dissolving. We always have to have both parts to have our solution. If I have a dilute solution, I have a very small amount of solute. If I have a concentrated solution, I have a large amount of solute. So something very dilute would be like watered down Kool-Aid. Something that is very concentrated, you could think of concentrated orange juice. If you just eat it right out of the can, it's very, very bitter or tart, I guess. And then you add water and it tastes as a solution that you are used to experiencing. Okay, so if we take a look at our air or natural gas, the air that you are breathing, the state of solution obviously is a gas state. The solute is a gas being dissolved into a gas. Vodka and water, not advocating this right now at this stage in your life, or antifreeze that we need very much now in our Minnesota winters, that the state of the solution is a liquid. How does it become that way? We have a liquid dissolved in a liquid. Oftentimes when we think of a solution, we are often thinking of a liquid, and you can see here brass, you guys know what that is. An example of that, we know that it's a solid. It actually is a solid dissolved in another solid. So your pop or your soda, if you think of your favorite one there, it is a liquid, but you have that carbon dioxide carbonation, the bubbles that you like to see, that's a gaseous state dissolved into a liquid solvent of water. So these are the things that we're going to take a look at and do some mathematical relationships with and some laboratory things. So this whole section here, we are going to skip right over because we are going to talk about these in class, a little bit easier to take and do these calculations. They're things you've seen before, we'll do them very quickly. So let's take a look, keep on going. We're going to jump into section 11.2 here. And we're talking about solutions. Well, how do things become a solution? How do we know, or how do things dissolve? You made Kool-Aid since you're probably really little. Well, how does that happen? Well, if you take a look, in your Kool-Aid solution, you have a solute and a solvent. And so we know our solute would be the sugar and the Kool-Aid mix, and the solvent would be the water. Well, in order for them to make this yummy solution that we have over here, something has to happen. There is actually a lot of chemistry here. And you should recognize that this is the change in heat, and we have to expand our solute. So we have to be able to find a way to, if there's a bond here, break the bond. And we also have to find a way to expand our solvent. If there's some sort of bond there, we're talking about hydrogen bonding or London dispersion forces or a dipole moment. We have to overcome all of those so that we can make our Kool-Aid solution. So we have to separate this. And you guys can see that in order to do that, it's going to take some energy. So if we look at the bottom, you can see that there's 3 steps in solution formation. The first step is separating the solute. This is going to mainly be an endothermic reaction. You got to take that energy in order for it to be able to expand the solute so that we can create some space. So it's mainly endothermic because we are breaking bonds. So if we think of NaCl, we know that that is regular old table salt. We know that that has a +1 charge and a -1 charge, and this is an ionic bond. There's a certain amount of lattice energy that has to be overcome in order to separate the solute. So then we are talking about overcoming those intermolecular forces. Intermolecular meaning within, to make room for the solvent. So we have to overcome the hydrogen bonding, the dipole-dipole, the London dispersion forces. And again, this is going to be mainly endothermic. So make sure you're jotting down that we need to overcome hydrogen bonding, dipole-dipole, and London dispersion forces. And then we need to form those bonds. We need to make our Kool-Aid. We need to make our solution. And so we're allowing the solute and the solvent to interact to form a solution. This is going to be an exothermic reaction where heat is being released. And the reason that heat is being released is because we are forming bonds. And so then if you look up at the top, we are talking about our result. So we have the change in heat of reaction 1, or step 1, change in heat of reaction 2, change in heat of reaction 3 to get our overall change in heat of our solution. So if we apply the things that we just talked about, we talked about that separating the solute was going to be an endothermic reaction. So endothermic, we know that that has a positive sign. We also said that expanding the solvent is going to be endothermic. And then we also took a look at that in order for these to combine, some heat has to be released. So you take in this energy to expand the solute, expand the solvent, they finally come together, and then you're going to have some energy released. Hopefully that makes sense to you. So now as we take a look at another diagram of this, it shows you this just a little bit further. So we have some different parts that we're going to show here. You guys can see on this side right here that we have our energy, our heat. You can see that here. And then we have the energy of the separated solute and the solvent. So that's step 1 and step 2 right here. Then we are releasing that energy. So this energy is being taken in right here, and then it's going to be released over here. Well, then we have overall change in heat of our solution. So this half over here is showing you an exothermic reaction. Well, if I take a look over here again, most things are going to be positive. As you can see, we have a blood drive going on. So we have this endothermic reaction here, and we have a little bit of energy being given off, but for the most part, the energy is remaining in the solution. And so this is going to be an endothermic diagram. All right, so I want you guys to jot a few things down underneath here. Now these two diagrams are going to play a part as to whether or not what type of compounds we are talking about. So if I talk about an ionic substance, an ionic salt, you should be recognizing when I say the word ionic that it is a metal to a non-metal. Well, if you think about the first step, our change in heat, and we have our ionic substance, and we are trying to get this reaction to take place. Well, this is going to be taking in a lot of energy. You have to overcome those lattice energies. So this is going to be very, very large, and it's going to be positive. It's going to be endothermic. I have to get over those strong ionic forces. Now we are talking about the water here for the solvent that's doing the dissolving. And if you think about that, water is extremely polar, but it has a lot of hydrogen bonding in between. Hydrogen bonding is very, very strong. And so this is going to have to take in a lot of energy again in order to expand the solvent. We got to break that hydrogen bond here between them. That doesn't mean that I'm breaking the hydrogen-oxygen bond. I am talking about this bond that happens between water molecules, the hydrogen bonding there. So I got to take a ton of energy so I can break that up. All right, and then my change in heat of step 3 is also going to have to be very large when this happens, but I am releasing a ton of energy. Because there's such a strong interaction between these ions, I'm going to be releasing a lot of this. Okay, so this is an ionic system. Well, what if I go over and now I'm going to talk about something that is nonpolar and has some water in it? Well, if I take a look at something that's nonpolar, my change in heat of a substance that's nonpolar, you know that there's not any interactions there of hydrogen bonding. We have some small London dispersion forces. So the amount of energy that this has to take in is very small because those London dispersion forces aren't very strong. And if I take a look at water, so this is going to be separating my solvent of water. Again, it should be the same thing. I have those hydrogen bonds to break, and so this is going to be a large endothermic exchange of energy. It has to take in a ton in order to break that hydrogen bond. And then just take a look, well, is my solution going to form? Well, it's going to have a very, very small release of energy. And there's going to be little interaction. Now, we always talk about that a nonpolar and a water substance doesn't dissolve. It does dissolve on a very, very small, minute scale, but for all practical purposes, we are going to say that the overall change in heat of this solution doesn't happen. It doesn't occur. Okay? Where over here, we know that ionic substance can dissolve in water, so this is a favorable situation. Okay, so the very last point that we want to make here before we stop this is if you take a look at this box, and in nature, remember that nature wants to be in the lowest energy that it can. Well, here we have this nice orderly box here on the left. I take this barrier out behind it, I shake it up. I think you can imagine that I'm going to have a box of everything that's the orange and the yellow balls are all going to be mixed around with each other. Well, what's easier for nature to do? Put it back in this nice orderly fashion, or to keep it all scrambled up and mixed up? Remember, nature says that increased entropy is very favorable. And so that entropy, that craziness is fine because it has lower energy. So if we can say that if our change in heat of our overall solution is exothermic, and the endothermic part is very, very small, then we know that our solution is going to form. So this goes back to the same thing that we've used before in the past, that like dissolves like. Nature desires a mixed state. Nature desires something that has very low energy. It favors solution formation. It favors this to happen because there's less energy involved. All right, that's our first couple of sections here. Hope you guys have a wonderful day, and I'll see you soon.